Greetings! Welcome to Electronic Circuits 1, lecture number 5. I am Razavi, and today we will look at the PN junction again, this time in this third region of operation, namely forward bias. If you remember, last time we talked about the PN junction in equilibrium and also in reverse bias, and today we will look at the third condition that could exist around the PN junction and see what it entails. As we will see, the PN junction in forward bias is actually the most interesting and the most useful regime of operation for the device. Now, before we go there, let's take a brief look at what we covered last time. So, we saw that a PN junction in equilibrium means that we have not connected the terminals to anywhere else. And as a result of the difference in the concentrations of electrons and holes, we will have some current flowing in the form of diffusion initially. But an electric field is developed inside the depletion region and eventually stops these currents. And what we saw is that because there is an electric field in this region, a potential difference, a voltage is also developed from here to here. And that voltage difference is given by this equation. This is what we call the built-in potential. And it's given by KT over Q, 26 millivolts at room temperature, times log of the concentrations on the two sides of the dopants, the phosphorus and boron atoms, for example, divided by Ni squared. And we saw that for typical doping levels, V0 is about 700 to 800 millivolts. All right, then we went to the PN junction reverse bias. And reverse bias is defined as applying a voltage from outside, as shown by this battery here, such that the positive side of the voltage goes to the N side of the junction, and the negative side of the voltage goes to the P side of the junction. That is the definition of reverse bias. And we saw that now that we have a positive voltage connected here, it wants to attract more free electrons from this region. So some free electrons go this way to the battery and leave behind positive ions. So the depletion region becomes wider. Similarly, on the P side. And that's really the only thing that happens. Once these electrons have been absorbed by the battery, any current ceases to exist, and we just have a simple situation like that. So we saw that even though there's no current flowing, no significant current flowing in reverse bias, this device is actually useful because we see that as the reverse bias voltage changes, so does the width of the depletion region. It becomes wider or narrower. So we saw that we can establish an analogy between what we have here and the capacitor with two plates. One plate is this conductive plate here, conductive material here, and the other is this conductive material here. And as we change this voltage, the capacitance associated with this junction changes. And we saw that it has this form as expected. For 0 volt applied, we have a narrow depletion region, meaning the spacing between the plates of the capacitor is small, so the capacitance is high. And as the reverse bias voltage increases in magnitude, the capacitance goes down. So that's the type of behavior that we expect. All right, so today we will consider the third condition for a PN junction, namely forward bias. And forward bias is the reverse of reverse bias. So let's see what that means. So today's lecture first will deal with the PN junction in forward bias. We'll get comfortable with that. We'll see all sorts of interesting things happen, and the device suddenly becomes very useful. It's very different from the devices we have learned in previous courses. And then we'll try to model the PN junction as a circuit element, so that when we have a PN junction inside the circuit, we can write equations for it. And finally, we'll talk about reverse breakdown, yet another effect in PN junctions. Okay, so let's look at the PN junction in forward bias. Well, we take a PN junction as usual. So here's our PN junction, N on the left, for example, and P on the right. And we connect a battery from outside. But this time the battery is connected such that its positive terminal goes to the P side of the junction, and its negative terminal goes to the N side of the junction. So the inverse of what we saw for reverse bias. So here's a battery, positive on the right, negative on the left, and we connect it like so to the PN junction. Okay, so now what happens? Well, let's call this VF for forward bias voltage. Well, we can see that we have a positive terminal connected to here. This positive terminal wants to push positive charge away from here. So it will push the holes that we have here to the left. Similarly, this negative terminal is connected to the N side. So it wants to push the free electrons on this side to the right. It wants to push them away. So we can say the electrons are pushed away from here, or they are attracted by the P side, by the plus side of the VF. In any case, what we see is that we begin to have a current of holes from right to left. So holes are flowing here because they are pushed away by the battery. And similarly, electrons flow this way because, again, they are pushed away by the battery. Can this continue forever? Yes, it can. What happens is that, for example, look at these electrons. The electrons start from here, flow this way, and come and get absorbed to the positive side of the battery. And this can go on forever. We have a current. As long as the battery can provide a current, this current will flow. Similarly with the holes. So we do have a current now because of the polarity of the voltage that we have applied from outside. And that's why we call this forward bias. We allow the current to move forward, so to speak. Okay, are these two currents opposite of each other, or do they add up? In other words, do they cancel each other, do they add up? Well, you can see that if electrons go from left to right, the conventional current equivalent is from right to left. If holes flow from right to left, the conventional current is still from right to left. So both of these actually contribute to the current. We have more current if we have electrons going this way and holes going this way than if you had only one of them. So both of these result in a current, a conventional current going this way. And this current can go on indefinitely. So that's interesting. We see that if we choose the voltage polarity like this, then we have a current through this junction. In reverse condition, in reverse bias, when the voltage was the other way, we didn't have any current. The current was very small. So that's a big distinction between what this guy can do and what resistors can do. For a resistor that we saw in basic circuit theory courses, we never thought about the current that goes one way or another. We always thought these two currents have to be following the voltage. So you change you go from positive voltage to negative voltage, the current goes from positive amount to negative amount. But now we see that it's a very different story. Okay. All right. So again, if I try to summarize what we have learned so far, this is what we see. If we look at the current that flows through the junction as a function of the voltage across the junction, this is what we see. Let's call this V, just V for now. And let's assume that V has this type of polarity, positive here, negative here, a voltage source. Maybe I should actually do it this way to make it very clear without any confusion. So let's take a variable voltage. If you remember an example like this 2 lectures ago, we take a variable voltage like this and we call it Vx, and then we measure this current Ix. And this is connected to N and P. So let's call this Ix and let's call this Vx. So from what we've seen so far, we can observe 3 types of operation. If Vx is 0, the junction is equilibrium, there's no current, we just have a depletion region inside. So we are right here. If a Vx is negative, you see, I have assumed the positive is on this side. So if Vx is negative, it means that this side is more negative than this side. This side is more negative than this side. So this side is more positive than this side if Vx is negative, which means this side wants to become more positive than this side, and that is reverse bias. So if Vx is negative, the current is very, very small. The only thing that really happens is that the depletion region becomes wider. On the other hand, if Vx is positive, so this side wants to be more positive than this side, like this battery case, then we actually have a current flowing. To make my notation accurate, I have to draw Ix on the other side. So this is Ix actually. So we see that if Ex is positive on this side and negative on this side, meaning it wants to make P more positive than N, then a current flows. So some sort of current will flow. And as Vx increases, we might expect that the current also increases. Now how it increases, we'll see in a minute. It's not a linear increase, not like a resistor, but in any case, it conducts. So here, for a negative voltage, meaning if P has to be more negative than N, there's no current conduction. We have only a depletion region that becomes wider or narrower. Whereas if P wants to become more positive than the N over here, then there is current conduction. So that's a very interesting device. Nothing like what we have seen before. Okay, so what is the expression for this current in the forward bias region? So let's just write here, this is reverse bias on this side. This is forward bias on this side, and right here it's equilibrium. And what we'd like to know is the current that flows in the forward bias region. Okay, so we will not prove the equation for the current in forward bias region. We'll just state it here and we'll use it. The proof is not that hard, and you can find it in many different books. But in the interest of time, and because we are really trying to get into circuits, we will not get tangled up in that proof. So I will write the equation here. So for such a device, we write I of the junction is equal to IS. We will talk about IS shortly, multiplied by exponential of the voltage applied divided by VT minus 1. So let's familiarize ourselves with all of these quantities. Ix is some sort of current quantity. Why do we need Is here? Well, because X doesn't have a dimension, 1 doesn't have a dimension, but this side has a dimension. So we need something here, and that's called Is. So Is has a name. Is is called reverse saturation current. It's just a name, don't worry about it too much. And then Vx is the voltage that we have applied across the junction, and Vt is the thermal voltage. If you remember, we said Vt is equal to, or is defined as Kt over Q, 26 millivolts at the room temperature. So this equation is what governs this plot here. Now, maybe again, to be consistent, let me change this junction to X so that we don't have any confusion here. So that current as a function of that voltage is given by this expression. Now, let's look at this. Let's take our time and get comfortable with this equation and see what it says. Well, when Vx is 0, how much current do we have? Well, x plus 0 is 1, 1 minus 1 is 0. We have 0 right here. So that makes sense. No voltage, no current. Okay? Assuming everything has settled down, all the diffusion currents have stopped, etc. Okay? All right. What if Vx becomes more and more positive? What happens? Well, this exponential grows rapidly. So we see that it grows rapidly. It becomes a sharp change in the current for a change in the voltage. So the dependence of the forward bias current through the junction upon the voltage that we have applied is an exponential function. So it's a very strong and sharp change. Okay, how about if we make Vx negative? Now, I didn't say this equation applies to reverse bias, but just out of curiosity, can we make Vx negative here and see what happens? Well, if Vx is negative, this term becomes smaller than 1, which means this overall term becomes a negative current. So that's interesting. This says that if you want to believe that equation, this is what we get. Right here, it becomes negative because this term is less than 1 when Vx is negative. Vt is positive, Kt over Q. All right. Now, if Vx becomes more and more negative, what happens? So let's say Vx is minus 2 volts. Vt is only 26 millivolts. Minus 2 volts over 26 millivolts is a very large and negative number. An exponential of a very large negative number is close to 0. So this term very quickly approaches 0 as Vx becomes more and more negative. That means that Ix approaches minus 1 times Is. So for very negative voltages, we just have this. And this value is equal to minus Is. And that's why we call this the reverse saturation current. It has saturated in the reverse condition to this value, minus Is. All right, so this is what the general characteristic actually looks like. Interestingly, even though this equation was perceived for forward bias, it does apply to reverse bias as well, only in predicting this amount of current that flows. You might call this a leakage current, because in reverse bias we said we shouldn't have a current, but we actually have a very small current. Now, generally when we draw this, we may draw it like this so that we remember there's a leakage current, but this value is so small compared to typical values that on a linear scale you would not be able to see this really. It would be very, very close to 0. But in any case, it's there and it's called the leakage current. So anytime we build a PN junction and reverse bias it, there is a leakage current. And in some cases, that leakage current is problematic. We have to worry about it. We have to remember it and take that into account. So it's important to remember that. All right. This equation plays a critical role in anything that contains PN junctions. So we really need to understand it well. We need to memorize it. We need to use it all the time. Sometimes we simplify this. Instead of Ix and Vx, maybe we may just write ID and Vd or different types of subscripts, but it doesn't matter. The point is that there's a reverse saturation current here, and there's an x minus 1 here. Okay. All right. Very good. This is the equation for example, the forward bias operation of the PN junction. Now, let me introduce one term that we will be using from now on. If we have a device that carries a current for, let's say, positive voltages across it and doesn't carry a current for negative voltages across it, that device is also called a diode. So, a diode is defined as a two-terminal device, so just like a resistor, except that it's a very strange resistor. Two-terminal device that carries current when its voltage is positive and no current when its voltage is negative. So is p-n junction a diode? Yes, p-n junction is an example of diode because it has very low current when the voltage is negative and has substantial current when it's positive. So we call this a diode. p-n junction is an example of a diode. There are many different ways to build a diode. Here's one way. So a lot of times actually we just call this a diode instead of a p-n junction, with the understanding that that is the definition of a diode. Okay? Now, if I have a two-terminal device, and I'm saying that when the voltage is like so, we have current, or the voltage is like so, we don't have current, somehow I have to distinguish between one terminal and the other terminal. For a resistor, we don't have a problem. When you switch the polarity of voltage, we also switch the polarity of current. But here, we need to distinguish between the positive terminal and the negative terminal. So, in other words, we have to distinguish between this guy and this guy. Now, in our circuits, we don't want to draw a p-n junction all the time. So we will create a symbol for the p-n junction that, first of all, is much easier to draw, much more compact, and second, it distinguishes between the N side and the P side, so that when we apply a positive voltage or a negative voltage, we know which one is which one. So the symbol for a diode is this. It has two terminals, and you see that the symbol is not symmetric. Remember the symbol for a resistor. It was symmetric. It just goes like this. So we don't know which terminal is which one. But here it's not symmetric. So this arrow is a visual aid for us. This arrow says current can go this way. This little line says current cannot go this way. So that's how we memorize it. Okay, so that means that if I apply a voltage like so, then it can conduct current, because with positive here, the current goes this way. So this is considered forward bias. And then if we draw it like this, but apply the positive side to the other side, then this will be reverse bias. This is something that we sort of have to memorize, that if the positive voltage, if this side is more positive than this side, we can have a current flowing this way. If this side is more negative than this side, then we can have no current. The current will be very small. It will be only this much. So that is the symbol for a diode, which we also use for a p-n junction. Okay. So if we try to establish a correspondence between what we see here and what we see here, it becomes clear. So is this terminal the P side or the N side? Well, remember, for forward bias, the positive of the battery has to go to P side. So for forward bias, the positive of the battery has to go to P side. So this terminal, or this arrow if you want, this terminal represents the P side of the diode, or the P side of the junction, And this terminal represents the N side of the junction. That's how we have to memorize it. And in fact, we even have names for these two terminals because they are different from each other. So the names that we use are, if you have a diode like this terminal is called the anode of the diode, and this terminal is called the cathode of the diode. You will probably not remember this in a few weeks or in a few years, but it's good to just hear it at least once, that this is the anode side, that's the cathode side. If you go for a job interview, they may ask you, what is the name of this terminal and that terminal? So you might as well memorize them. All right. Okay, so from now on, we will use this symbol for this big monster. So it will be a lot easier to draw it inside our circuits. It's a two-terminal device, and it behaves like that. All right. Let's look at this IS again. I just need to mention one important point about IS before we move on. All right, so we see that the terms inside this exponential do not depend on the structure that we have. In particular, they do not depend on whether this is silicon or germanium, because Vx is the voltage we apply from outside, and Vt is KT over Q. And they do not depend, this exponential does not depend on the doping levels. So are we saying that the amount of current we get for a given voltage is the same whether we have a silicon p-n junction versus a germanium p-n junction? That sounds not quite right, because we know that they have different band gap energies and all sorts of things. So also we're saying that this doesn't depend on doping levels, which is also strange. So all of those are actually reflected in IS. IS has that information in it. So let me write the equation for IS. IS is like this. A times Q times Ni squared multiplied by dN over Ln. I don't remember these equations very well. Okay, so we have the doping level, acceptor doping levels, and then we have dP over doping levels of donors times LP. Lots of constants running around this equation. Don't worry too much. We don't use this equation very often, but I wanted to point out a few interesting facts about it. So, what's A? A is the cross-section area of the diode. So, cross-section area of the junction. What do we mean by that? Well, when you build this junction, it's not a two-dimensional structure, it's a three-dimensional structure, right? So it has some area through which the current flows. That area is called A. So if you were to build a p-n junction in 3 dimensions, it would look like this. So it would have N here, P here. And then this area is what we call A. So that's the cross-section area through which the current flows. Does it make sense that the reverse saturation current, IS, or generally the current, is proportional to A? Yes, it does make sense, because just like a resistor, as I make this cross-section area bigger, I can accommodate a larger current for a given voltage. So it makes sense that IS, and therefore the total current flowing through the diode, are proportional to the cross-section area. So that is fine. We got an extra line here. Let's try to erase that line. Okay. So we're happy with A, the cross-section area. And in fact, that was the most important point I wanted to convey here, that the total current that flows through a diode is proportional to the the junction area or the cross-section area of the p-n junction. That's something we always have to remember, just like a resistor. Okay, Q is electron charge. Ni is the intrinsic density of electrons and holes, and it is Ni that distinguishes between germanium and silicon. If you remember, there's a band gap energy here, and that's why we get different numbers for silicon versus germanium. And then we have some stuff here. These are the diffusivities of electrons and holes, as you remember before. Na and Nd are the doping densities on the two sides. And then on top of that, we have Ln and Lp. So these are called diffusion lengths. And we'll just leave it at that. We don't have to worry about it too much, what diffusion length means and what does it do, etc. So don't worry about that, but I just, in case you're wondering, that's what they are. So again, we see that the saturation current and therefore the total current do depend on the doping levels that we have on the two sides. They depend on the diffusivities and so forth. So now we can see all of the dependencies that we have. Ultimately, it is really this equation that's of interest to us, but we do need to remember that this is proportional to A. Now, why do I insist on that? Well, because when you look at typical diodes that we use in practice, their junction area, the cross-section area, can assume a very wide range. You have diodes that have very, very small areas. This junction area might be half a micron by half a micron or 1 micron by 1 micron. That's inside integrated circuits. Whereas you could have diodes that are very large. For example, in power electronics, in cases where we need to carry very large currents, for example, hundreds of amperes, then this area has to be extremely large. It has to be maybe centimeters by centimeters. So that's why we need to remember that IS is proportional to the cross-section area. Okay, that is what we have here, and I believe it is time for a quiz. But before we go there, I just wanted to make one interesting note. So this is a note that we will bear in mind from now on. So please write that for yourself. All right, so what happens as Vx becomes more and more positive? Well, this exponential grows. If this exponential grows and becomes much greater than 1, then we can safely drop this 1 and write the current as Is times x bar Vx over Vt. All right, so under what condition is that approximation reasonable? Well, if Vx is about 4 times Vt, this exponential is large enough. So we will say that if the forward bias voltage is greater than 4 Vt, approximately speaking, we have Ix approximately equal to Is x bar Vx over Vt. So that's a good equation to remember, and in most cases this is what we will use. Why? Well, how much is 4 Vt? Vt is 26 millivolts, so 4 times 26 is 104 millivolts. So this is 104 millivolts. And as we will see, in most practical applications, the voltage that we have across the diode is on the order of 700 to 800 millivolts. So that means that this exponential is gigantic, right? It's orders and orders of magnitude greater than the exponential that we get with 4 Vt. So we are way up here, and that means that we can safely neglect this 1. So from now on, anytime a forward biased diode is forward biased, a p-n junction is forward biased, we will assume that the relationship between the current and the voltage is just Ix exp of Vx over Vt. You always have to remember this one, but as engineers, we have to know when to make which approximation. Okay, so let's write the quiz here. I would like to keep all this stuff while I write the quiz so that you can refer to this information. So here's our quiz of the day. We have a PN junction, and we apply a current in this direction from outside, a constant current, call it I1. The current wants to create a forward bias because it wants to push this way. It wants to push positive charge this way, which means the device will be forward biased. The question is, if we inject a current of I1 in this direction, how much voltage do we get from here to here? So how much is the voltage across the diode? I will give you 90 seconds to think about this. All right, did you figure out what happens now? Well, we are in the forward bias region, and we said that in the forward bias region, the device is dominated or defined by one equation, and that's this equation here, or this equation here. This equation holds in forward bias regardless of whether we are applying a voltage and measuring the current, or we are applying a current and measuring the voltage. The relationship between the two must hold. So if we are looking for the voltage, we just go back to our equation, or even the simple equation, and we say we are looking for Vx in terms of Ix. So we just divide by Is, take the natural log of both sides, multiply by Vt, and that will give us Vx. So we can say Vx is equal to Vt log of Ix over Is. And that is the equation relating the current and the voltage in this form. So that's also an important equation. You have to remember both this equation, now without this one most of the time, and then this equation, again without that one. And this equation says that the voltage that you measure across a junction when it is forward biased and it carries a current of Ix is given by log of Ix over Is multiplied by Vt, 26 millivolts. Keep in mind that Is is constant when we buy that PN junction. These are all properties of the PN junction itself. They are not under our control from outside. This is the area, that's the intrinsic density. These are all properties of the semiconductors inside. So we don't have any control over it. And that's the certain value. Now, depending on how much current we apply to it 1 milliamp, for example, then we will get a certain voltage, let's say some amount, which we will soon see actually. Okay, now that we have a good handle on the PN junction in forward bias or a diode in forward bias, we can look at an example just to get comfortable with some numbers. So let me add a page here, and we will see a simple example. Okay, so this example has two parts. In part A, we assume if IS is equal to 10 to the minus 16 amperes. You can see it's a very small value. That corresponds to a very small diode, 10 to the minus 16 amperes. And we measure a forward bias current of 1 milliamp. What voltage is applied to the diode? Okay, so it's very simple. I bought a diode and I connected the battery to it in forward bias. So positive goes to the anode, negative goes to the cathode. There's a certain voltage which I don't know, so we'll just call it VF. And I measured the current, and the current is 1 milliamp. And then I looked in the data sheet of the diode, and the data sheet said IS is 10 to the minus 16 amperes. So now I'm curious to see how much voltage I have applied. Okay, so we know the current, we know IS, we need the voltage. Remember the quiz? So what we do know is VF, the forward bias voltage, is equal to VT log of ID, or I, divided by IS. And I is 1 milliamp, and IS is 10 to the minus 16 amperes. VT is 26 millivolts at room temperature. So that will give us approximately 778 millivolts. All right, so that's the amount of voltage we need to apply to obtain that amount of current. These are typical values, 10 to the minus 16 or minus 17 amperes for IS of a diode, and a bias current of 1 milliamp, a forward bias current of 1 milliamp. These are typical values that we see in most electronic devices, except when you go to, for example, high power applications where these currents are much, much larger than 1 milliamp. Very well. The second part of this question is, okay, now one point that arises here is that in writing this equation for the bias voltage, I have assumed that that 1 is negligible with respect to the exponential. Is that a good approximation here? I just made that approximation and moved forward. I can double check and see. So we know that this is 778 millivolts. So if the voltage applied to the diode is 778 millivolts, how much is the current? Well, we have an exponential. And that exponential will be exponential of 778 millivolts divided by 26 millivolts. Remember that? So we have this term here, exponential of 778 millivolts divided by 26 millivolts. And you're welcome to calculate this. You see that this is gigantic. So it's much greater than 1, So it's a safe approximation that we have made. Okay, in part B, we asked the following question. I performed this experiment. I applied a voltage of 778 millivolts, and I obtained a current of 1 milliamp. Now, what if I want to increase the current by a factor of 10? So, how much should the voltage increase to raise the current by a factor of 10? Okay, that shouldn't be that hard. So instead of 1 milliamp, I want 10 milliamps. I plug it back in here, calculate, see how much voltage I get, right? So, but let's write it in a more general situation, see what we get. So we have VF1 for the first current level, let's say 1 milliamp, was VT log of I1 over IS. I1, for example, 1 milliamp. Now, if I want to go to 10 milliamps, 10 times, I'll call that VF2. So VF2 is VT log of I2 over IS. I2, for example, 10 milliamps. I1, for example, 1 milliamp. Okay, so we're trying to see how much the voltage should increase. So in other words, how much is VF2 minus VF1? Well, what we can see is that VF2 minus VF1 is equal to the difference between two logs times Vt. The difference between two logs is the log of the ratio. This Ix cancels with this Is. So we end up with log of I2 over I1. So if I want to increase the current by a factor of 10, meaning this is 10, the voltage increase has to be Vt log of 10. So for 10x increase in current, we need to increase the voltage by Vt log of 10, which is approximately equal to 60 millivolts. This is a beautiful result. It's a number that is good to remember at all times. It says that if we have an exponential device, which is the case with a diode, in order to increase its current by a factor of 10, all we need to do is increase its voltage by 60 millivolts. Every time the voltage goes up by 60 millivolts, the current rises by a factor of 10. So if we plot I as a function of V carefully, so ID as a function of VD. I hope you are not confused by my notation that keeps changing. ID is the diode current, VD is the diode voltage, right? Okay, so what we are saying is that if we are somewhere and we have a certain current, we have some voltage, so we call this, for example, VF1. Then to raise this current by a factor of 10, so 10x increase, requires only 60 millivolts of change. So we move up by 60 millivolts, the current goes up by a factor of 10. So that's the interesting thing about the device. And again, if you go by another factor by another 60 millivolts, this goes up by another factor of 10. So it goes to 100 milliamps. And that's the property of an exponential function. So that's very important and interesting to remember. Okay. All right. So this also tells us something else. If the currents that I use in practice in my field are all on the order of 1 milliamp, 2 milliamps, 3 milliamps, 4 milliamps, 5 milliamps, maybe 10 milliamps, in that range, I am not dealing with very high currents or very low currents, then I can say that the voltages that I will observe across forward bias diodes in my field are approximately known, are approximately what we calculated before. So if we go back to previous page, we calculated for typical doping levels the voltage to be, okay, I'm sorry, it's actually this page. We calculated the voltage for typical values of current and IS to be about 778 millivolts. So we say that because the currents that I'm dealing with are not so divergent, they are from each other, they're different from each other by a factor of maybe 4, 5, 10, then I can say that the voltage across forward bias diodes is always approximately 700 to 800 millivolts. So we say that typical forward bias voltages for diodes are in the range of 700 to 800 millivolts. That's a good approximation, because if you come along and say, I have a diode whose voltage in forward bias is 1,000 millivolts, 1 volt, I would be extremely surprised. Why? Well, because that's 200 millivolts above this. 200 millivolts increase in voltage. 200 millivolts increase in voltage. 60 millivolts, 60 millivolts, 60 millivolts. Every time it goes up by a factor of 10. So if you have a diode that has 1,000 millivolts across it, then that diode carries a current about 3 orders of magnitude larger than the numbers that we are dealing with here. Right? So instead of 1 to 10 milliamps, we're talking 1 ampere to 10 amperes. And such diodes do exist, but they are not what we are considering in our application. And in fact, for those diodes, if you have a diode that is designed for 1 ampere, you will not have an IS this small, because that diode will be large in area, in junction area, so its IS will be large. Okay? So in most applications, it's a very good estimate to assume that the forward bias is in this range. This is important because when we get to solving circuits using diodes, we do need to pay attention. We need to have some sort of number to start with. Otherwise, the computations become much more complicated. All right. Now that we have this, we are ready to go to the modeling of the PN junction. So let's talk about the modeling and see what we should do. PN junction or the diode. All right, so we said that instead of drawing the whole PN junction every time, we just draw it like this in a circuit. So we have other stuff around this, maybe resistors, capacitors, other things. And now we need to solve that circuit. We are given a circuit consisting of these devices, and we are asked to find currents, voltages, other types of characteristics. So how do we go about doing that? Well, our first reaction might be, if the diode is in reverse bias, it doesn't have much current, it's just a capacitor. If the diode is in forward bias, it has a current, and that current is given by an exponential, as we saw before. So maybe that's how I should look at it. So we can start with what we call an exponential model. Which is quite an accurate model if we know IS. So here's the model that we had before graphically. So ID versus VD. From now on, I will use I diode and V diode. And here's what we have. In reverse bias, there's a small amount of negative current, but we don't worry about it too much. So, and we will say that ID is equal to IS x of VD over VT. So we dropped that 1. We know that the exponential in practice is much larger than 1, so we don't worry about it anymore. Very well. So from now on, every time I have a diode in a circuit, if I know it is forward biased, I replace the diode with this equation. I write that equation for the current and the voltage of the diode. Does this diode satisfy Ohm's law? No, of course not. Ohm's law says I is equal to V over R. This one says I is equal to something times an exponential of the voltage. So obviously it's not a resistor. Not to mention that, of course, in this direction it doesn't even have a current. So it is far from Ohm's law, and we have to stick with this equation. Okay, so we have an exponential equation that tells us the relationship between the current and the voltage of a diode when it is forward biased. If it's reverse biased, if we know it is reverse biased, then we can just replace it by a capacitor or just say there's no current, so it's an open circuit, right? All right, so let's look at a simple example to see how friendly this equation is in our calculations, in our circuit calculations. So here's an example, and let me change the color of my pen, maybe to this. I have a resistor and a diode and a battery. Very simple. A resistor of value of R1 and a battery of value VB and a diode. I will call this diode D1. So from now on we'll use the letter D to represent diodes, just the way we use letter R for resistors. So I connected a battery and a resistor and a diode in a loop together. And what I would like to find is the current that flows through this loop. So how much current do we have here? Is it 1 milliamp? Is it half a milliamp? Is the diode forward biased? Is the diode reverse biased? All these things. Okay, so when we are given such a circuit, the first thing to do is not panic, right? The second thing to do is not write equations. The third thing to do is to look at the circuit and try to feel what the circuit is doing first, before we jump in and start writing equations. All right, so we look at the circuit, we look at the battery and how it's connected to the diode. We say, well, the positive side of the battery is connected through a resistor to the diode, and the negative side is connected to the diode. So it is likely that the diode is forward biased, because this positive wants to go all the way to the diode. So we guess that the diode is forward biased. We don't know, but we guess. We guess, we assume, and we write our assumption somewhere to make sure that we don't forget about it. And then we go through the calculations based on that assumption. At the end, when we have solved the circuit and we have found the results, we check to see if our assumption was correct. If it was, great. If not, it means that that assumption was wrong. We have to make a different assumption. So we'll start by saying assume D1 is forward biased. Now, are we 100% sure that the diode is forward biased? Maybe not, but it's a good educated guess. It is likely that it's forward biased. We'll solve the circuit and then at the end check. Okay, so if the diode is forward biased, then what do we do? Well, we cannot write Ohm's law for the diode. The diode is governed by this equation, not by Ohm's law. But the resistor is governed by Ohm's law. Okay, so if this current is called Ix and it flows through R1 from left to right, it generates a voltage across R1 according to Ohm's law. So there will be a voltage from here to here equal to Ix times R1. That's what Ohm tells us. It says if you push a current from left to right, we generate a voltage equal to that current times that resistor, and that voltage has its positive end on the left and its negative end on the right. Okay, how about this voltage, the voltage from here to here? Well, we don't know how much it is. We'll just call it VD1. So the voltage from here to here will be called VD1. All we know is that VD1 and Ix are related by this equation. Why Ix? Because the same current that flows through the resistor has to flow through the diode. It has nowhere else to go. If you write a KCL at this point, we see that Ix comes out of the resistor and has to go into the diode. So all we know is VD1 and Ix are related by this equation because we are assuming forward bias. Okay, how do we relate all of these? Well, we can write a KVL around this loop. The KVL starts from here. We're going from negative to positive. So we write minus VB. We're going from positive to negative. We write plus IXR1. Then we're going from positive to negative. Right, plus VD1. We are back to where we started, so the result is 0. Remember, what we are looking for is Ix. Ix is unknown. So now we replace VD1 with the equation that we derived before. Remember, we used this type of equation, Vt log of, we used this type of equation. So we'll say minus VB plus Ix is equal plus Vt log of the current through the diode. How much? Ix divided by the reverse saturation current of the diode. This is equal to 0. This equation tells us everything we need to know. So I need to solve this equation to find Ix. Now, how do I solve this equation? Well, this equation does not have a closed form because Ix appears as a linear term here and as a log term here. So how do we solve it? Well, by iteration. If we know the value of VB and the value of Is, and Vt is 26 millivolts, we can make a guess for Ix, see what happens, and we iterate until Ix is obtained accurately enough. And that's the value of Ix. Now, once we do that, once we find Ix, if Ix happens to be positive, then this assumption is correct. If the Ix happens to be negative, then this assumption is incorrect. I can tell you that because we have a positive connected to the anode of the diode, this diode will be forward biased, this assumption is correct, and Ix will be positive. But the point of this example was really one thing, and that is, if we use the exponential function to represent the diode in our circuit analysis, we very quickly reach equations that are not easy to solve. This is with only one diode, one battery, and one resistor. You can imagine what happens if we have several diodes or some more complex network. then the equations very quickly become unmanageable. We can always use a program to solve these equations. You can write a C script or a MATLAB script or something to solve these, but we cannot do them by hand. And if we cannot solve a circuit by hand, we cannot develop insight into how it operates. And that is a valuable piece of information that would be missing. So we have to make an effort to create a different model, not just exponential model, but a different model that allows us to carry out these calculations more easily, especially when the circuit is more complex. And that model exists, and that's something that we will talk about in the next lecture. So in this lecture, we saw that we talked about the forward bias region and the fact that it's an exponential relationship. But next time we will look at a simplified model that doesn't have this exponential in it, but it allows us to attack more complex circuits. I will see you next time.